Welcome back to the Carbon Nanotube Intro to Houdini mini-series. If you missed part 1, that's fine. If you already know your way around the Houdini interface and how to navigate okay, then you can probably just jump right into this video. However, if you're brand new to Houdini, then you might want to check out part 1 to familiarize yourself with some of the basics. In this video, we're going to get started on our carbon nanotube by creating not a nanotube, but a related structure called buckminsterfullerene. It's a molecule made of 60 carbon atoms, and because it's spherical, it turns out to be a perfect cap for our carbon nanotube, or at least half of this buckminsterfullerene, or buckyball for short, no relation to the magnetic toys. Because we like to be scientifically accurate, we're going to be paying careful attention to the arrangement of the carbon atoms and the bonds between them. So let's jump into Houdini and get creating. So this is where we left off last time. We created a ground plane to put below our carbon nanotubes, but we're going to be creating a new geometry node. So we're going to put our cursor in the network view here, hit tab, and start creating a geometry node. This is just an empty geometry node. We can call it buckyball. And we'll dive in either by pressing I or just double clicking on the geometry node. And now we're in SOPs land, as we talked about last time. And now we have to make some geometry for our buckyball. We have 60 carbon atoms to create that need to be placed precisely. So brace yourself for a little bit of work. We're going to hit tab again and create a platonic solid. Here we go. Just a quick note about the visibility of objects. Right now we're zoomed way out, and that's because if we click up here and ghost other objects, we can see a ghost of the other ground plane that we have in our scene. But if we just want to ignore that for the time being, which sometimes things can get in the way, we can click hide other objects. And then if we hit in the viewport, if we hit space F, that's going to frame up on the platonic solid that we created. It's a tetrahedron. Okay, instead of a tetrahedron, we're going to choose soccer ball, and that's it for the arrangement of atoms that we need. The soccer ball has the same 60 points or corners as the atoms in buckminsterfullerene. These little lines here you probably won't see. Those are just some normals that I had displayed visibility, so I'm just going to click that to turn those off. And sometimes it's nice to name our nodes, so we're going to call this soccer ball here to remind us what we've created. Okay, since we've done a tremendous amount of work already, let's take a pause for a few minutes and talk about geometry itself in Houdini. I think geometry components in Houdini are one of the more foreign aspects. So let's dig in and get a little uncomfortable in order for us to get more comfortable again. In other 3D applications, we have vertices, edges, and faces as the basic components of geometry. So that should be the same in Houdini, right? No. If we get our select tool here by hitting S or clicking the arrow, it's true that we do have edges here. We can select them. But edges in Houdini are kind of second-class citizens. They're not that important, and you can kind of forget about them for now. Edges, schmedges. What about vertices? Well, they look like vertices, but they're not actually called vertices. They're called points. If we hover over here, select points. Is that just semantics? Points, vertices, same difference? Not quite. You see, we also have vertices in Houdini. You see, the vertices aren't shared at a single point. There's kind of one unique vertex around each point. So it's a little bit different. Now in Maya, you have things called UVs, and these are a little bit like that. UVs, even though they're related to a single vertex, you can kind of split them out in the UV editor and have them in different pieces. And that's a little bit the same. And indeed, vertices in Houdini are related to things like UV mapping. And we're not really going to deal with that much in this series. So like edges, we can mostly ignore vertices as a component type. Let's turn our attention back to the points. Points in Houdini are one of the most important types of geometry component. We're going to be dealing with them a lot. At their most basic, a point in Houdini represents just a position in 3D space. Let's look at what this means by using a new panel in the interface that we haven't seen yet. It's up here in this row of tabs, the geometry spreadsheet. But because I like to see it at the same time as the scene view, I'm actually going to split this panel in two so I can see them together. So I'm going to come up here, and I'm going to go split pane top bottom. You can also use the Alt close bracket here as the hotkey. And now we have two scene views. So I'm going to change this one by right clicking on the scene view, coming down to inspectors and choosing geometry spreadsheet. Now we have a spreadsheet of each of the 60 points on this soccer ball, numbered from 0 all the way down to 59, and we currently have number 37 selected. We can also show the point numbers on the right side of the scene view here by clicking the display point numbers, and we can see that indeed we've got number 37 selected. What do the numbers in these columns represent? Well, for each point, it's the 3D position in X, Y, and Z. Position X, position Y, position Z. That represents where this point is in space. The capital P is short for position. What's fantastic about the geometry spreadsheet, it looks a little dry, but it gives you a really good insight into all the data that you have going on in your scene. And as we go on, we're going to have more and more complex types of data. You can also change between the component types here. So next up, we have the vertices. And you can see that, again, this is a little strange. We have this sort of 2-number index of where the vertices are and which point number it corresponds to. Again, we're not really going to be dealing with vertices much, so we can kind of skip over this. You'll notice there's no edge spreadsheet. Again, edges aren't really first-class citizens. They're sort of a derivative component type represented by a connection between 2 points. Again, we can mostly ignore edges for the time being. Finally, we get to the second big important type of component. Faces, right? Well, not really faces. These are called primitives. We can choose the selection up here. And I'm going to turn off the point numbers for a minute. So yes, they're kind of like faces. They look like faces and they act like faces in many ways, but they're called primitives. Primitives are a big part of Houdini, and you can think of them like a single unit of geometry, a thing, an entity. In this case, they're basically faces, but we'll see that there are other types of primitives we can have. This soccer ball has 32 primitives, 0 to 31. We can also see a summary of the geometry of the soccer ball by middle mouse clicking, holding down on the node itself, or we can click this I node info button and it'll pop up and actually stay up. So we have 60 points, 32 primitives, and it's calling them polygon primitives, and that's as close as Houdini is going to get to calling them faces. The info panel also tells us about the data associated with the components in here, the point attributes and the primitive attributes. So attributes are data connected to points and primitives and vertices. Attributes, points, and primitives are the core of Houdini in many ways, which is why I'm spending time here on this now. It may seem kind of abstract and confusing, but the sooner you start thinking about Houdini and geometry in terms of points, primitives, attributes, the quicker you're going to get up to speed in creating your own things. So again, attributes are data associated with the different geometry components. So the point attribute is P. We saw that here. It's position in the spreadsheet. CD is the primitive attribute. Now what could that be? I'll give you a few clues. So it represents some kind of data or property of the primitives. And in the spreadsheet, we can see there's a couple of different values. There's 111 and 000. If we look at the attribute itself, we can also see that it has 3 components, R, G, and B. Have you guessed it? It's the color of the primitive. 111 for white and 000 for black. So that's defining the color of these polygon primitives. CD stands for color diffuse. Most people just say color. CD is a common attribute that you might want to remember. And it's worth noting that these attributes are case sensitive. So if you have to refer to them in Houdini, capital C, lowercase d, and capital P for position. Okay, so we've been introduced to some of the fundamental parts of Houdini. Let's actually do something with that. Okay, so the first thing I want to do is I don't actually care about this color attribute, so I'm going to delete it. I'll hit Tab and type in delete attribute, and we get an attribute delete node. I'm going to click to put it down, and I'm going to connect it up here. And under primitive attributes, I'm going to type in capital C, lowercase d, hit enter, and we can see in the spreadsheet that CD attribute is gone. But we still see the color here. So this is a difference between what we're seeing in the viewport and the spreadsheet. And that's because the geometry spreadsheet reflects the node that's currently selected. If we select the soccer ball, CD is back. Attribute delete, it's gone. And the blue flag represents what we can see in the viewport. So we want to click over here, or the hotkey is also R, and we can see that the color is now gone. We've just left with the default gray shader. If we wanted to recolor the primitives, we could drop down a color node. Shift enter to make it connected to the previous node and have that display flag on there automatically. I'm going to change the class from point to primitive because I want to put the color attribute on the primitive. And I could choose just a random color. And now you can see each face, each polygon primitive, is colored randomly. And we have the CD attribute here in the spreadsheet. We can see all those colored values. I don't actually want to do that, so I'm going to get rid of that color node. What's next? Well, if I'm actually making a buckyball, I don't really care about the primitives. All I care about is the points, the position of the points. So I can actually get rid of that geometry. How do we get rid of the primitives? Well, if we were in another application, we might go to select primitives, drag over them, and hit the delete key. And they get deleted. And in fact, you can see over here, we've created a new node called a blast, which is a fantastically named node. And it's a node that's used for getting rid of geometry. But we wanted to keep the points. We didn't want to get rid of everything. So I'm going to delete that, get rid of that. You could also hit undo. And we're going to create a new node. Now, it turns out there is a node that we can use to get rid of primitives but keep points. And this is when it's great to be living in the age of Google, because you wouldn't necessarily know which node to use just by searching through these menus. It would be kind of unintuitive, because certain nodes in Houdini can do a variety of things, and sometimes they have little hidden secrets that let you do interesting things that you wouldn't find out unless you're searching for how to solve a particular problem with Google. How do I get rid of geometry but keep the points, sort of thing. This is kind of like if you're a programmer and you're always looking at Stack Overflow for frequently asked questions. Google is your friend. Fortunately, there's a fantastic community of people answering tons of questions and will give you insight into how to use so many different nodes in Houdini. So anyway, it's called the add node. See, told you wouldn't guess it. So the add node is great for adding geometry. You can create new points, you can connect them together in polygons, but it also has this little checkbox that just says delete geometry but keep the points. And that's all we want to do. So now the primitives are gone. You can see in the primitive spreadsheet we don't have anything, but all the points are still here, which is great. So thinking about our goal, what we want to do is we want to put an atom at the position of each point on that soccer ball. How are we going to do that? Turns out there's a great node for doing that. It's called copy to points. Copy to points. Copy to points has two inputs. We have one input, which is the target points to copy to, and that's what we've created, so we can wire that up. And the other one says geometry to copy. What do we want to copy? Well, an atom is spherical, so let's create a sphere. Tab, type in sphere, and drop it down here. And we can drag that into the first input here. And if we put our blue display flag on here, okay. Well, the spheres are too big, but we've successfully put all of the spheres on each point. How big do we want them? Well, carbon atoms have a van der Waals radius of 1.7 angstroms. In Houdini, I typically use 1 unit is 1 angstrom, and I highly recommend you do that too because it makes importing molecular data so much easier. So what we're going to do is we're going to change our uniform scale from 1 to 1.7, represented by 1.7 angstroms. Okay, that kind of made the situation worse. The spheres are bigger and we actually wanted them smaller. What's the problem here? Well, it turns out we didn't make our original soccer ball the right size. So I'll put the display flag back on the soccer ball and let's think about how big we want our soccer ball. I'm going to move the geometry spreadsheet down a little bit here. So what radius do we want the soccer ball? We could look up what the radius of buckminsterfullerene should be, but there's another point of data that's even more useful, and that is the bond distance between carbon atoms. It turns out the bond length between carbon atoms should be about 1.42 angstroms. Well, how are we going to figure out what that corresponds to if we have this length as 1.42 angstroms? There's different ways to do it, but I've made myself a little helper tool called point distance. For the scope of the lesson, I'm not going to go into how I made the tool, but as soon as you get more familiar with Houdini, you're going to start finding yourself making little extra tools that are going to make your life easier. In many ways, Houdini is software to make CG generating tools. So this tool takes 2 points. I'll wire it in here, and I'm going to show the point numbers so we know which points we're looking for. I mean, 0 and 1 will work just fine. The distance between 0 and 1, it turns out, is currently 0.38. So we're going to go up, boost our radius here. And now we have to kind of keep going back and forth between this. So what I can do is I can click on the point distance and just put the pin icon here. And that's going to keep this panel up here. And then when I click on the soccer ball, I can hit the P key and that'll pop up a tiny little parameter pane here. And so I can have sort of both of them visible at the same time. So it turns out we're looking for something about 3.65. There's if you're wanting different position with the slider, Houdini has a great virtual slider. If you hold down the middle mouse key, you get this ladder of different precision values. So you can, while you're holding down the middle mouse button, you can go down to the 0.01 and drag it back and forth. Or you can even go down to 0.001 and drag it back and forth. And then you're going to get really precise value. So I'm going to go down to here. 3.67 turns out that's going to be doing just fine. I can hit P to hide that parameter pane again, and I'll make sure to unpin this so that when I click on other nodes, I get the parameter pane updating. So let's check out our spheres again. Let's go down to the copy to points, hold down R and click on it to put the display flag on there. And I'm going to zoom out. Okay, so the spheres are still overlapping, but it turns out this is actually an accurate representation of a space-filling model of where the atoms are. These atoms are covalently bonded together, so they're sharing electron clouds. But another nice representation for this kind of thing is called ball and stick, where the atoms are shrunk down, and so we can see sticks connecting them, representing the bonds between them. So we're going to try and go for something like that. So we could arbitrarily decrease the uniform scale here, but what I like to do, because I know that that's the correct van der Waals radius, is I'm going to put down another transform node in between to act as a separate sort of scale multiplier. So I can hit tab and look for the transform node. And the transform node is a very common useful node that you're going to want to use. I can drag it into here and you can see that the lines sort of hook up automatically as I get close. Release that, and now I can change the uniform scale independently and go down to something like, I don't know, 0.3 for our ball and stick representation. And I'm going to just call this our scale multiplier. So in many ways, the transform node is like the transform parameters we had at the object level. I hit U to jump up here. I'm going to hide the ground for a sec. So we also have scale controls on the object itself, but as you can see, that's just scaling globally that whole object. Whereas if we're going down in here with a SOP, we can scale whatever components we want to. So you're starting to see kind of how we're working in a sort of non-linear way. We can kind of work backwards and forwards and add things in beforehand and afterwards. All the information flow is maintained, so changes we make up here flow down and update the final result. It's a very liberating way of working. You don't have to have everything figured out at the beginning. You can kind of work backwards and forwards, slowly building things up over time. Okay, at this point, let's drop down a null node to mark the end of our network. If we accidentally connect it to something else, we can just click and shake it and it'll get disconnected. And we're going to put it in here, put the display flag on here, and I'm going to call this out buckyball to represent the end of our network, our final buckyball result. We're not done, but let's just do a check-in on the kind of geometry we have here. So I'm going to click on the I node info on this null. So we got 60 points, so far so good, 60 primitives, 60 vertices, 60 spheres. Okay, so the 60 spheres kind of make sense, but isn't a sphere made up of a bunch of points and primitives on its own? What's going on here? So it depends on what kind of sphere you've made. So if we go back up here to the sphere and click here, we can see that we've made a sphere of type primitive. Remember how I said a primitive is different from a polygon or a face? It's a bigger concept. It represents a single unit of geometry, whatever that geometry might be. In this case, instead of polygon primitives, we've made a sphere primitive. I mean, they couldn't really have made this more confusing, could they? So the primitive type is primitive, but we know that the type of primitive is a sphere, and you can change a different type of primitive to something other than a primitive. Well, let's not worry about the terminology too much. Let's just worry about what's happening in the viewport and what the information panel is showing. Let's make the sphere type polygon. I'm going to uncheck the display point numbers because it's completely obscuring what we're looking at. I'm going to put the display flag on just the one sphere, and I'm going to open up this info panel and pin it so that we can keep it up there. Okay, so with this one sphere now, we have actually 42 points, 80 primitives, of type polygon. Okay, so these are polygon primitives on this individual sphere. That makes sense. We can increase the frequency and add more. We'll just refresh the panel. Now we go 362 points, 720 polygons. Okay, we could also change this to polygon mesh, which might be a more familiar layout. Again, points and polygons, but now we have this sort of row and column layout. Okay? Okay, and there's even others, but to avoid deeper confusion, we're just going to stick with the ones that we've talked about so far. So what does this mean for our buckyball? Which one should we choose? Okay, let's go back to our null output and click on the info panel. When we had the sphere type primitives, we had 60 of each. Now we have 16,000 points, 17,000 polygons. But this kind of makes sense because we've copied our original sphere 60 times. And as you could imagine, this is going to take a lot more resources to display in the viewport and to render out. As you get more and more and more geometry, eventually your system's going to bog down. So you're probably better off with the primitive type, which is going to be very, very lightweight. But there are two potential problems. Maybe your rendering engine doesn't know how to render a sphere primitive, what that is. So I use Redshift, and I believe it can render out sphere primitives and other primitive types, but maybe there are special things you want to do with the rendering that doesn't support sphere primitives, for example. And secondly, what if you're not copying spheres, but you're copying something else, like boxes? We can come create a box or a cube, and instead of the sphere, we can pipe that directly into our network. Now, we still have polygon primitives instead of sphere primitives. And it turns out the box doesn't have a type primitive box. The most basic you can get is just a polygon cube of 6 polygons per cube. So now again, we're getting more complex with that cube copied 60 times. So there's a very powerful function in Houdini called packed primitives. Now it sounds scary, but it's a fairly simple idea. So before we pack our geometry, let's just check here. So we've got 480 points and 360 polygons. Okay, so now let's go up, and after our box and scale multiplier, we're going to put down a node called pack. So we're going to wire that in here, and we're going to check back on our null output. And now again, we have 60 points, 60 primitives, and they're of type packed geo. I know we're straying from our scientifically accurate buckyball, but this is actually really important. We're talking about geometry types here. So what happened here? Why do we have 60 packed geos? So essentially what's happening is this pack node is packaging up all of the geometry that's coming into it. We can put the display flag here into one individual unit. It's just one thing now. It's packed into a single primitive. And this packed primitive can contain whatever you want. We can put the sphere back in, we can change it to type polygon, we can increase the frequency, so it's a whole bunch of polygons as the input, but the packed unit is just one single thing. It takes whatever complicated geometry you have, and if you're going to be copying it a whole bunch of times, it's going to pack it into one little thing so that it's much more lightweight to display and render, and it saves a lot of memory. So a quick useful tip, if we want to compare before and after we have the pack, we can disable this node. And the hotkey for doing that is we select it and hit B, or you can also click this flag here called bypass, B for bypass. Now we've bypassed that node, and again, we've got thousands of polygons. And we can hit B to re-enable that node, and we're back down to our simple 60 geometry. So this is essentially what I do when I'm creating molecules, is I pack a sphere and copy it to points. So you're already halfway to creating your own PDB molecule importer. Okay, so let's color the atoms black. We'll add a color node. I'm just going to put it at the end. We could put the color node in various places, but I'm just going to stick it at the end here, and let's make them black. There we go, black atoms, like the superhero. All right, so we just went through a lot of theory. Time to stand up and stretch. Now let's finish our buckyball. All right, I want bonds connecting each of the atoms here. Now I found 3 ways to do that, and I'm going to show you all 3 because this is a tutorial, right? You're here to learn, right? Cool. Okay. So first up is the wireframe node. So I'm going to drop down a wireframe node. And if we wire that in after the original soccer ball, I'll show you what that does. We can put the display flag here, And that looks like what we need, right? It's sticks connecting each of the points. But we don't have too much control here other than the wire radius. Because the wireframe actually creates sphere primitives and tube primitives, and that's not exactly what I want, I'm just going to move on to the second method. Okay, and that is called convert line. Here we go. And I'm going to connect it after the color delete node here. Okay, so what has that created? It looks like edges, but are they edges? What are they actually? They are polygons, 90 polygons. This seems strange. We're not in wireframe mode. These are just floating lines. We had 32 polygons to start, and that makes sense. But now we have 90 polygons. So this confused me for quite a long time. I've done a little bit of math, and I'm pretty sure I know a polygon when I see one, and these don't look like polygons. So this is Houdini being Houdini. What you can think of these as polygon curves, each little short curve segments. What exactly is a curve? Let's take a little detour for a minute. Let's create a curve node, drop it down, put the display flag on our curve node, and in the viewport, I'm actually going to go into the top viewport. You can also hit 2 in the viewport. So with the curve node selected, it says here left click to add point. So I'm going to click, 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 and hit enter to complete. Okay, and we've got 5 points and 1 polygon, okay, because we've got our curve type to be polygon. See, the only difference between a polygon that we're familiar with and this polygon curve is whether or not it's closed. What? When I said this confused me for a long time, I literally just tried to take the time to understand this while I was creating this tutorial. So back to our convert line here, I'm going to hit space 1 in the viewport to get back to perspective. What we've essentially done is converted a whole bunch of closed polygons into a series of open polygons, each of which is just connecting 2 points. And there's 90 of them. Anyways, even if you don't fully understand that or don't believe me, that's okay. We can still use that as the input for a node called polywire, which is essentially like an extrude operation. So we're going to come down to polywire, wire it up here, put the display flag on it, and now we have even more polygons. We can change the radius to something like 0.2, and we can change the number of divisions around here, something like 8. Also, you can see that the geometry is kind of connected at these corners, and I actually want it to be disconnected. And how we can do that is we can change the smooth point from 1 to 0. And now you can see that they're all disconnected. And there's a couple of reasons for that. One is if you wanted to do any render time tessellation smoothing, or if you wanted to put down a subdivide node, we could subdivide it. And if we had that still connected, you can see it gets all weird and not what we want. Okay, so I'm going to get rid of that subdivide. So this will just preserve the edges and only smooth around the tube, if that makes any sense. Now you may be thinking, I'm getting in way too deep and technical with all this polygon curve stuff. Does it really matter as long as it works? We can just create things. The answer is yes, it matters, and I'll tell you why. If we look at this input node here, it says polygons to wire. So what that means is if we had a NURBS curve, and we wanted to wire that into the polywire, it'll do precisely nothing because it's expecting polygons. If instead we change that to polygon, that works. So if we wanted a NURBS curve, we would have to convert it somehow with a convert node, or what I often do is put down a resample, which does the conversion on its own. And if you think about it, this takes polygons as input. We don't actually need this convert line. If we just wire this in directly, we get the exact same result. We're creating polygons and converting that into polywires around each polygon. Closed polygons, open polygons, they're treated the same. That's pretty neat. Okay, I bet you're sick of making these bonds, but I'm going to show you one more method, and the reason is that that method is what we're actually going to be using for our final full carbon nanotube. So what we're going to do is after the add node, we're going to create something called connect adjacent pieces. And what we want to do here is we want to connect adjacent points together. So our add node just had points on its own. And the connect node, if we change this from adjacent pieces from points just to the regular adjacent points type, and if we increase our search radius, then it's going to start creating open polygons between each point. So something like 0.75 works. The search radius is going to have to be a little more than half of what our bond length is, just because that's the radius that it's searching in. So in essence, this is doing a very similar thing to the convert line, but we're just approaching it in a different way. And we can steal the exact same polywire node. We'll just bring it in, and now we've got our bonds again. So why do it this way when you could just go straight from polygons to the polywire? Why this extra step? Well, what if you never had any polygons? What if all you ever had was a point cloud? So now we've got our bonds here, and we've got our atoms over here. But we can only put the blue display flag on one of them at a time. How do we merge them together? Merge. So merge is also a very handy node, which allows you to bring threads of your network together so you can have all of this geometry in one spot. So we're going to go from our copy points into the merge, and we're going to go from our polywire into the merge. And you'll notice that this doesn't have individual input dots like other nodes do, 1 or 2. This has infinitely many, which means you can put infinitely many things into the same node. You can reorder them here, and all that's going to do is just change the order of the points and primitives and where they show up in the geometry spreadsheet. Let's put the display flag on. And sure enough, we have our final buckyball. We'll pipe that into our color, and there we go. So again, clicking on this final buckyball node, let's look at the geometry in the spreadsheet. We have rows that correspond to atoms, and we have rows that correspond to bonds, but there's no real clear separation between them. In the primitive spreadsheet, we might be able to see a little bit clearer. We've got those packed spheres, and we've got other stuff that isn't packed. It would be nice if we had like a label or a tag or some way that we could differentiate between our atom primitives and our stick primitives. This is one of the many functions of groups in Houdini. Now groups in other applications, you might think of them as collections of objects. But here in Houdini, a group can be a teeny tiny collection of maybe just 1 or 2 points and nothing else. So a group node is a collection of components, and it can be only one type of component, either primitives or points or edges. Ooh, edges trying to reassert themselves as an important component type. Anyways, we're going to choose primitives, and we're going to put it under the copy to points here to collect all of the atoms. We can call it atom prims, and we can make a selection, but by default, if we don't select any primitives, it's just going to grab everything that's coming into that input point. Another quick little tip here, we can click Alt drag and bring out a copy of that and just stick it under the polywire. And this is going to be our bond prims or stick prims. And again, that's going to collect in a group everything that's a bond primitive. And when they get merged together, if we select our final output, in the primitives tab, you can see we have these new groups. Atom prims and bond prims. If it's 1, that means that the primitive is in the group. 0 means it's not. So all the atoms are yes in the atom prims group and not in the bond prims group. And if we get down to these, now these are all the bond primitives. If we go to our selection tool and we select primitives, and there's another option here that says select groups. If we click on that, we can see that we have our atom primitives and our bond primitives, and we can kind of keep them separate that way. So that's a nice little organizational thing we can do. One final optimization here. If we check one more time at this info panel, we can see that we have 2 primitive groups. There are 60 atom prims and 720 bond prims. That's because we've packed the atom primitives. Wouldn't it be nice if we could pack each bond into a single entity? That's all we need, right? Like one bond is just kind of one thing. So we could do that on this side. We could add in a pack. So after the polywire, let's try putting in the pack here. But now, that's just creating one single primitive. That's not what we want. What if we put the pack above the polywire? No, that doesn't do anything either. So the pack is just trying to create everything into one. That's not really what we want. We want each individual bond to be a packed primitive. Let's get rid of the pack. Fortunately, can you guess what I'm going to say? There's a node for that. So this one's called assemble. And if we put assemble after the polywire, what it's going to do is it's going to look for connected pieces. And if we click this checkbox here, create packed geometry, what it's going to do is it's going to create packed fragments. Kind of like packed primitives. They decided to call it something slightly different. So there's 90 primitives, packed primitives. And that's one other reason that we wanted to disconnect the geometry here. If it was all connected, we would have just one packed fragment. But because they're discontinuous, then we can have them as individual things. And now here we go. We can check their final output. We have 60 packed geos, which are the atoms, and 90 packed fragments, which are the bonds. And at long last, we have a nicely optimized buckminsterfullerene molecule. Give yourself a pat on the back. Honestly, what we've just gone through in this lesson is some of the hardest material involved in learning Houdini for the first time. I'm not going to pretend all of that material was easy or straightforward, but I hope that I've helped you over some of the bumpier aspects involved in Houdini. There's still plenty of challenges ahead, but if you feel like you have some kind of grasp of points and primitives and manipulating them, then you're well on your way to building your own things in Houdini. If you're still feeling a bit lost, that's okay. I invite you to rewatch some sections of the video perhaps and play around and experiment on your own. Look at the spreadsheet, the geometry spreadsheet, and see what's happening. Middle mouse and look at this info panel here. Look at the kinds of geometry that you're creating and see if you can understand what's going on. And we're going to be doing some really fun things in the next lesson, I think, so I hope to see you there. If you learned anything at all, you have to give this video a thumbs up. That's in the YouTube terms of service. Otherwise, let me know in the comments what I can do better, and please consider subscribing to Making Biocinematics. It really helps me out. Thanks so much for sticking with me right to the end of this video, and feel free to click over here. Feel free to click over here if the next video in the series is up. I hope to talk at you again soon. Bye.